Hey, in the previous chapter, we talked about the concept of magnetic flux, but we haven't really used it yet. So let's consider this scenario. Now, here I have a piece of wire that is bent into the shape of a C, kind of like a square. So this C-shaped piece of wire has a height y, and let's take another metal bar and let's set this metal bar to lie between the top and bottom horizontal segment of this C-shaped piece of wire. And this metal bar, let's suppose we're able to move it to the left or to the right. So this is a movable metal bar. That in principle we could slide to the left or to the right as we want. Now, for the moment, this movable metal bar is going to be a distance x away from the vertical part of our C-shaped piece of wire. Now, let's also set up a magnetic field that is pointing out of the board. So here's a magnetic field, and this magnetic field will just be uniform everywhere. We want to deal with a simple magnetic field. So here's my magnetic field. I'm going to call this magnetic field B. Okay, at this moment in time, we could ask the question, how much flux is passing through this area that is enclosed by the C-shaped bar plus the movable metal bar? So right now, I could say the magnetic flux is going to be B times A. So magnetic field strength times area times the cosine of the angle between A and B, but they're both going to be directed in the same way, so we get times cosine of 0. Now, the area of the loop that we're considering is just length times height, so that'd be x times y. So I could write that magnetic field as BA becoming B times x times y. And I'm going to call this my initial flux. So this is phi B initial. Initial magnetic flux. Now let's suppose we take this metal bar and we're going to slide it to the right. So I'm going to slide the metal bar to the right until it is over here. And the distance I'm going to slide the metal bar, I will call delta x. So this distance is delta x. Now I have a final magnetic flux. So after I take the bar and I slide it over to here, I could call this the final magnetic flux, and the final magnetic flux I could write that as phi B is equal to, okay, again we have B times A times the cosine of theta. B is going to be the magnetic field. That never changed in this problem. The area has increased. The area used to be x times y. Now the area is x plus delta x times y. So I could write that as B times x plus delta x times y. So I could say that in in some amount of time, delta t, the magnetic flux went from an initial value to a final value. So in time delta t, because it does take some amount of time to move the bar from its initial position to the final position, I could say we had magnetic flux initial was B times xy, magnetic flux final was B times x plus delta x times y. So I could say that we had a change in magnetic flux. The change in magnetic flux is going to be the magnetic flux final minus the magnetic flux initial. So let's find out what this change in magnetic flux is going to be. So I could say, okay, final is that value, initial is that value. So I have the change in magnetic flux is going to be b x plus delta x times y minus bxy. And now I will just get rid of this parenthesis by factoring in the b and the y there. So I get the change in magnetic flux is going to be bxy plus b delta xy minus bxy from this last term here. And I notice bxy minus bxy, these two terms end up canceling each other. So I found that the change in magnetic flux is b times delta x times y. So in a short time, the time it took to move the bar from its initial position to its final position, the magnetic flux changed by that amount. So if I want, I could write that the change in magnetic flux over that time, the rate of change of magnetic flux, well, if we're talking about the rate of change, we would have the change in magnetic flux divided by the change in time. So that would be delta phi b, delta t. Well, delta phi b we found as being that. So we have a b, a delta x, and a y divided by delta t. Now, if I look at this equation, I could just rearrange some of the terms in the fraction. So I could write this as being equal to b times y times delta x over delta t. And if I look at this problem with what's going on, you move a distance delta x in a time delta t. That's basically the speed at which you're moving. So I could write the change in the rate of change of magnetic flux as rate of change of magnetic flux is going to be b times y times v, where v is the speed at which the rod is moving. So I'm going to take this equation. I am not yet telling you why this equation is going to be interesting. I'm just saying let's take this equation and see what we could do with it. So we'll come back to this equation in a little bit. Now, let's consider something else we've dealt with for a while. We said that a charge in a magnetic field, that if the charge is moving in a magnetic field, the charge will feel a force. So we'll come back to this. So we said a moving charge in a magnetic field will feel a magnetic force. So where are the moving charges in this problem? Well, we said before that the bar itself was made out of metal, and metal contains electrons in it from the C electrons. So the electrons in the metal bar are going to feel a magnetic force because the electrons in the metal are moving in a magnetic field. So we said we had F equals QVB sine theta for the magnetic force, and we use the right-hand rule to find the direction. Of the force. So I'm going to redraw this movable metal bar, but I'm going to explicitly draw the electric charges that are located inside this bar. So here is our bar in the magnetic field that is moving. We still have this magnetic field everywhere. And it doesn't matter. I said in nature, what we have is we have electrons residing in the bar from the C electrons in the metal. I could just as well as think of positive charges in the bar, and that's fine for the purpose of what we're doing. So here is our bar that is going to be moving, and I'm going to draw some positive charges inside the bar. So here's my positive charges inside the bar. And the bar is moving with a certain velocity in that direction, to the right. So we could ask the question, what direction is the magnetic force going to be on these charges? Well, we use the right-hand rule. We take our right forearm, we align it with V, we curl our fingers towards B, and I find the magnetic force on these charges is downward. So there is going to be a magnetic force pointing down on all of these charges. F magnetic.